For this example, we're going to find a power series solution near x naught. Here, our x naught is given to be 1. So we're centering not at 0, but at 1. So the solution will look slightly different. So we know that the solution we're seeking is y equals the sum starting from 0 to infinity of a sub n x minus x naught to the power n, where x naught represents the center. So we want to replace that with 1 in this problem. So that way the solution we're seeking will looks like this. And if you were to expand and write out just a few terms, so the first term is a0, then the second term is a1 x minus 1 to the first power, plus the next term is a sub 2 x minus 1 to the second power, plus a sub 3 x minus 1 to the third power, and so on. So it goes on. Now, our goal is to figure out what are these coefficients. Of course, a0 and a1 are arbitrary, but we need to figure out a2 and a3. And you can find more coefficients if you like, but you'll see where this is going. So let's go ahead and plug these expressions. We need the first derivative and the second derivative of our assumption. This is our assumption. So let's go ahead and compute its first and second derivative. So we know if that is y, then the first derivative is the sum starting from n equals 1 to infinity of n times a sub n x minus 1 to the power n minus 1. And we know the second derivative will be the sum starting at 2 to infinity of n times n minus 1 a sub n times x minus 1 to the power of n minus 2. Now we're going to substitute these expressions into our given differential equation right here, and right here. And then we'll take it from there. So we have the following. We have the sum. So we have x times the second derivative. So that will be the sum starting from n equals 2 to infinity of n times n minus 1 times a sub n times x minus 1 to the power of n minus 2. So that's our expression for the second derivative plus the first derivative. So that's going to be the sum starting from n equals 1 to infinity of n times a sub n x minus 1 to the power of n minus 1, plus the last term will have x times y. So that's x times the sum starting from 0 to infinity of a sub n x minus 1 to the power of n, everything equals to 0. All right, now let's clear this up. Now, if you like, you can actually ignore the indexing. I did mention that in class to my students, but you can keep them. You'll see the work is pretty much the same, but if you ignore the indexing, you'll get to the same recurrence formula either way. So, but let's, for formality, we'll keep indexing and then you'll see where this is going. But do try it out without keeping track of the summation and you will arrive at the same recurrence formula. So let's keep going. Now, if our centered was 0, then we would be able to push this in and adjust the power. But since we're not centering at 0, we do have to do a little substitution so that algebraically we can adjust the powers. So we're going to do the following substitution. Let's introduce a variable. Let z stands for x minus 1. So I'm letting z to be replaced with these pieces so that way we can actually algebraically work it out. So if z is equal to that, that means then x must be equal to z plus 1, just solving for x. Now with that substitution, keep that in mind. So now our summation becomes the following. So x is replaced with z plus 1. So we will have z plus 1 times this summation starting from n equals 2 to infinity of n times n minus 1 a sub n. Now x minus 1, we're replacing that with z. So this will be z to the power of n minus 2. Plus, now the second summation, we just rewrite the term in the parentheses. So we still have n starting from 1 to infinity. N times a sub n, now z to the power of n minus 1. And the last sum, we're going to again replace this x with our new substitution. So that's z plus 1 times the sum starting from 0 to infinity of a sub n z to the power of n. equals to 0. All right, so that clears out a lot of things. Now let's continue on algebraically. So we're going to break the first summation, this one right here, into two pieces. So we're going to distribute the sum to the z and then to the 1. So we're going to have two summations from that piece. So you'll have z times the sum starting from n equals 2 to infinity of n times n minus 1 a sub n z to the n minus 2 plus, now distributed to 1, you will have just the sum itself starting from n equals 2 to infinity of n times n minus 1 a sub n z to the n minus 2. Then the second one, that doesn't change, so we're just going to rewrite this. So just to save some time, I'm just going to copy and paste it right here. So that's the same thing as we have above. The next one, again, we're going to do the distribution. So we're going to distribute the sum to both of these terms. So we have plus z times the sum starting from 0 to infinity of a sub n z to the n, and plus the last term we distributed to 1, so we just have the sum itself. So n equals 0 to infinity a sub n times z to the n equals to 0. All right, so the heavy duty is over. Now let's combine the powers. Now I'm going to go ahead and push this one right inside, combine the power. The second one, there's nothing to be done. The third as well, nothing to be done. The fourth one, we're going to again adjust the powers with this one. So let's take care of those two summations for this one and this one. So we have the sum starting from n equals 2 to infinity of n times n minus 1 a sub n z. Now this will become the power n minus 1. And the next two remains unchanged. So I'm just going to go ahead and copy this to the next line. So we have these two guys as it is. So let's just try to fit it right in here so we don't overlap too much. So this is the next line. And then plus, now the next one I highlighted, as you can see on the corner, as we move this inside and combine the powers, you're going to get the sum starting from 0 to infinity of a sub n z to the power of n plus 1. The last one remain unchanged. I'm just going to rewrite that. The sum starting from 0 to infinity of a sub n z to the n equals to 0. All right, so now we want to group all of them into a single summation. But before we do that, we want to make sure all the z's have same powers. So it looks like this one, we need to come up with the substitution. So is this one, and this one, also that one. So we're going to try to have them all have same variable. Let's introduce a dummy variable. Let's come up with k. So for the first one, we're going to let k be the exponent, n minus 1. If that's the case, then n will be k plus 1. Again, just solving for n. For the second one, I'm going to let k to be the exponent, n minus 2. So that means n would be k plus 2. So that's for the second piece. The third piece, we're going to let k to be n minus 1. So n would be k plus 1. The next one, we're going to let k to be n plus 1. So n would be k minus 1. And the last one, we just change k to an n. All right, so let's do the following rewriting. So the first summation, we have the sum. Now, if n starts at 2, then that means k will start at 1 to infinity, and n is replaced with k. So this is going to be k plus 1, and then n minus 1 will simply be k. We have a sub n, which is again k plus 1. We have z to the power of k. Plus, now the second one, we're going to get n is k plus, so we have the sum. If n starts at 2, for this one, k will start at 0 to infinity. So n is replaced with k plus 2, and n minus 1 is replaced with k plus 1. A sub n, that will be k plus 2, z to the k. The third summation, we're going to have n starts at 1, so k will start at 0, since n is k plus 1. And then the inside we will have n, so that will be k plus 1 times a sub n, that will be again k plus 1, z to the k. Now the last two, let's write them right here. We have the sum, n starts at 0, but since n is k minus 1, so k will start at 1 and go to infinity. We'll have a sub n is k minus 1, z to the k, plus the last summation we will have n is exactly k, so k will start at 0, all the way to infinity, a sub k, z to the k equals to 0. All right, so at this point, we are ready to group them together, but since we're keeping track of where each sum starts, we want to write out the terms so that they all start at the same place. But up to this point, you should be able to group them all into a single summation if you did not keep track of the indexing. So I'm going to go ahead and rewrite a few terms. So for example, this one and this one, they start at 1. So there's one step ahead of the other three summations. So we're going to go ahead and write out the first term for this summation, and this summation. Once we write out the k equals 0 term, then they're all ready to start at k equals 1. So that's what we're going to do on the side. So when k equals 0 for the first one I highlighted, you're going to get 2 times 1 times a sub 2 plus the second one that I highlighted. If k is equal to 0, you're going to have 1 times a sub 1 plus, for the last one I highlighted, if k is equal to 0, you have a sub 0. All right, so those are the first term of the summation. Now they're all ready to start at k equals 1. So we have the sum k equals 1 to infinity. Let's rewrite them all. So for the first one, they all have x to the z to the k, I'm sorry. So that means I can just pull that out, write out their coefficient. So this is for the first one. For the second one, I'm just going to go ahead and just erase these. We have, these are the coefficient of z to the k. So let's put that next. The third one, we're going to have these coefficient for z to the k. So I'm trying to write down all of their coefficients so that way we can factor out z to the k. The third one, the fourth one, we have a sub k minus 1, and the last one, a sub k. Everything has z to the k equals to 0. All right, so now we're going to equate the coefficient. The left-hand side, we want these guys to be 0. And then we also want the coefficient of z to the k, which is all of this, to be 0, so we can find our recursion formula. So if I set these guys to 0, so we have 2 times a sub 2 is equal to, so let's set them to 0, so you will see one more step. Plus a sub 1 plus a sub 0 equals to 0. So that's one piece. The second piece is taking the coefficient of the term z to the k equal to 0. So we have k times k plus 1, a sub k plus 1 plus k plus 2, k plus 1, a sub k plus 2, plus k plus 1, a sub k plus 1, plus a sub k minus 1, plus a sub k. So those are the coefficient of z to the k. We set that to 0. So that will give us our recursion formula. We will be solving for the highest subscript, which is this one right here. So let's, now this is not so important because eventually you're going to get that from your recursion anyway. So, but since we have it, let's solve it anyway. Solve for the highest subscript, which is a sub 2. So a sub 2 would be negative a sub 1 minus a sub 0 divided by 2. So that's one of our coefficient. Now, let's get the recursion formula. So if I were to solve for a sub k plus 2, I subtract everything. So you will have k plus 2 times k plus 1 times a sub k plus 2 is equal to minus all of these terms. So you'll have minus k times k plus 1, a sub k plus 1. Since I factor out the minus, I will take care of that as I'm subtracting. And the minus the third term, that will be again plus k plus 1, a sub k plus 1, plus a sub k minus 1, plus a sub k. And then we divide that by these coefficients to isolate a sub k plus 2. So So our a sub k plus 2, it's going to be negative all of these guys. So you have k times k plus 1, a sub k plus 1, plus k plus 1 times a sub k plus 1, plus a sub k minus 1, plus a sub k all over k plus 2 times k plus 1. Now, since I see the same subscripts appear twice, I can kind of combine their coefficients and simplify the recursion formula. So we have, so distribute the negative as well. So you have negative k squared minus k minus 1. So these are the coefficients that you see right here, this one and this one, distributing the negative. And then you can combine. So pull out the negative. I guess we didn't really need to distribute it. So this is k squared plus 2k plus 1, which can be factored into k plus 1 squared. I'm going to replace that in there, and then that will be our recursion formula. So these guys are combined. So that would simply be just k plus 1 squared times a sub k plus 1 plus all of these guys right here. And then all of it divided by k plus 1 times k plus 2. So this is our simplified recursion formula to give us the coefficient. Now we're going to start k equals 1, 2, 3, and so on. You could start at 0, but since we already have a sub 2, we don't have to start this at 0. We can start at 1 to save you some time. So there you have it. Now let's use this to get one more coefficient. So if you look at our solution form, so we know this is what we're after. Eventually, we want these guys right here. So A0, A1, those are arbitrary. A2, we already have it. Now let's go for one more. You can compute more once you got used to it. You start having fun. But I'm going to go ahead and just for simplicity, we're just going to go for one more coefficient. So if k is equal to 1, I can find a sub 3. So that would be negative. So k is 1, so this is 2 squared, that's 4. 4 a sub 2 plus k is 1, so this would be a sub 0 plus a sub 1 all over 3 times 2. So that's our a sub 3. Now let's simplify this a little bit further. So you have negative 4 a sub 2 over 6 minus a sub 0 over 6 minus a sub 1 over 6. So I just separated and distribute the negative. And now here I can simplify 4 over 6. So that's going to be 2 over 3. So let's just write that right here, 2 over 3. And now I'm going to go ahead and replace what a sub 2 is in terms of what we got previously. So that's right here. So I'm going to replace that down there. So this would give me, so the negative cancels out. So you'll have 2 over 3 times a sub 1 plus a sub 0 over 2 minus a sub 0 over 6 minus a sub 1 over 6. Now let's combine and we'll simplify this. So this would give us a sub 1 over 3 plus a sub 0 over 3 minus a sub 0 over 6 minus a sub 1 over 6. And you can combine now, like this one and this one, they can be combined. So that will become 1 a sub 1 over 6 plus, and then these also can be combined. So that's, again, a sub 0 over 6. So there you have it, your coefficient a sub 3. So now we're ready to write down our solution. So we know our solution looks like this. So this is what our solution looks like. And the goal was to compute these coefficients, which we successfully did. So I'm going to go ahead and plug them in very carefully. So this is our solution. So A0 and A1, what they're arbitrary, so keep them as they are. A2, I'm going to replace that with what we computed. So we found that to be right here, negative A1 minus A0 over 2. So this will be negative A1 minus A0 over 2. That's that. And then a sub 3, we also computed that right above, as you can see. So this one, I'm going to replace it with a1 over 6 plus a0 over 6. So that's that coefficient. Now let's group our solution so you can see what is y1 and y2. So I'm going to go ahead and collect the terms. So our final answer will look like this. So collect the terms with a0. So you have a0 times, so the first term is 1. The next term that appears for a0 is right here, times x minus 1 to the second power. So you'll have minus 1/2 x minus 1 to the second power, plus the next place a0 appears is right here. So that's 1/6, because a0 is factored out. So 1/6 x minus 1 to the third power, and keep going, there are more terms. Plus, now we're going to collect the terms with a1. So here's a1. The first term that appears with a1 is this one. So we get x minus 1. Plus, the next term appears with a1 is right here, negative 1/2. So I'm just going to put a subtraction right here. Minus 1/2 x minus 1 squared. Plus, the next place we see a1 is right here, 1/6 times that factor. So it's 1/6 x minus 1 cubed plus dot, dot, dot. So there you have it. This is your solution centered at 1. And as you can see, your two infinite series are right here. So this is your y1, and this is your y2. Now, there's one thing I forgot to mention, that right here, when we assume that z is equal to x minus 1, eventually when you write out the solution, you replace these pieces with z, but eventually, of course, we replace them with x minus 1. So that's what I forgot to mention earlier. So before writing down the solution right here, you will have your solution in terms of z, but finally you replace them back with the original variable x minus 1. And this will be the final step. That's how the solution would look like. All right, I hope this helped. Try out another example and see how you feel. I'll see you next time. Take care.